Yes. Oh, nice to meet you. What's your name? My name is Milani. Sulani. Sulani. Okay. I'm Mila. Nice to meet you. Nice to meet you. Do you have like a promote the crypto coffee? Yes, I think this time we celebrated crypto cafe. Most of the yeah. It's interesting. It's interesting. So are you also a PhD student? Probably, yeah. Yes. Yes. What is your field? What do you do? What is your field of study? Like, what do you? Cryptology. Cryptology. Yeah, that's super interesting. We do also crypto, but from a little bit more from the engineering part. Like, okay. For example, I try to make, like some of the schemes, like for example, curve 448 and 8448. That was the last thing that I was working on. Make it faster, also it's more on the engineering side, like just to speed up, to make the energy consumption very low and stuff like that. So you're from which university? From this one, but just the engineering part. Ah, okay.
So, are you ready? Is she coming? No. Hi. You want to mute the mic? I think I'm muted. Yes. Yeah. Okay. I guess we can start. So welcome to this first this crypto cafe. It's not the first session of the new semester, but it's the first enlarged, so maybe virtual. We're hoping to have also people not only physically present here, but a little bit from the outside world. Get interested into the nice things that people do here at the FAU in cryptography. So today it's our great pleasure to have a guest, a famous guest who's visiting us from Tampere, but an American, so Billy Brumley, who's going to talk to us about side channel analysis and lattices. So thank you very much for accepting our invitation and looking forward to the talk.
Francisco, thank you very much for the introduction and also for the invitation to speak today. It's nice to speak. A little bit about myself. So I've been in Tampere for 8 years now. I'm a professor there. Before that, I've spent a few years in product security at Qualcomm, where I was an engineer, and I did my PhD. I finished that at the end of 2011 from Aalto University in Finland. So I'm kind of an engineer. At the same time, my background is in theoretical computer science. So I would like to think that I understand some theory parts of computer science as well. So it's a pleasure to speak today. This is going to be a pretty informal talk. But yeah, let's dive in. Sort of the math part of this are the lattices and the side channel analysis. My specialty in terms of research, I've been doing side channel analysis for a long time. I towards 15 years maybe. So as an engineer, side channel analysis is a very applied topic. And at the same time, I try to use a lot of the theoretical constructions that we get from the math and the theory side. And I'm going to talk about how hard that is to do today. Right, so let's jump in. Lattice attacks, it can be based in any kind of group where you can do DSA style or even Schnorr. I don't mean Schnorr, I mean Elgamal type signatures. But I think for an example today, elliptic curves is a really good example to run with. If you don't know elliptic curves, that's okay. We're actually not going to use the elliptic curve part of it at all. Okay, so I'll try to spend a couple of minutes on this slide. So we have an elliptic curve, EFP, which so you have a curve that's defined over some finite field for a large prime P. And so the curve itself, this is kind of legacy elliptic curves. This is the stuff that's been around for more than 20 years now. A and B are fixed coefficients of the curve. Okay, so you have a degree 3 equation in 2 variables. So this is all of the XY solutions over GFP. So all the XY solutions to that equation defined over that finite field. You take all of those points along with the, well, engineers would say it's very artificial identity element, and you get a group. That's the idea. We're building a group. Okay. And since we have a group, you get all the typical, it's a cyclic group, abelian group. So you get all the typical things that you might think you get with a group. So G here, in terms of notation, G is the generator. So it's a point on the curve, which generates a large prime subgroup. And the prime is going to be N. Okay, so that's the order of the prime subgroup. So those are all fixed parameters, A and B, T, and N. We're also, so the idea is to produce a digital signature here. Here it's done with ECDSA, but like I said, any kind of group nonce Elgamal type signature is going to fall into the same bucket here, okay? So we have a long-term private key here. It's alpha, so it's an integer between 0 and N, okay? And that's fixed. So as a user, you'll generate that once and you keep it for yourself. I'm really sorry I changed the notation this morning, but I forgot to change this D. This is alpha. So you have the private key alpha, and then the public key is alpha times the generator. Okay. In a multiplicative group, this would be exponentiation. Here it's written, we write the group additively with elliptic curves. Right. So then to sign a message, you generate for each signature that you want to sign, you generate a new one-time key. So that's what nonce means here. It's a number used once, and it's from 0 to N. And the signature consists of 2 components, which are integers modulo N. You have the R component, which is you take that nonce K, you multiply it by G, and you take the X coordinate, and you reduce that modulo N. And you take the S half of the computation is, this is a hash function. So you compute some one-way function over the message. So the message is public. So you hash the message and you add in the private key times the R component that you just computed, and then you divide by the nonce K, you reduce that modulo N, and the signature is RS. Why that works is not relevant at all for this talk. And even the R component is totally irrelevant. Even the elliptic curve is completely irrelevant. This entire talk is going to be focused right here on this S component here. And I think it's really nice for a talk because really to understand this, you don't have to know anything about cryptography. You don't have to know anything about elliptic curves. You have to know very little about abstract algebra. This is just a linear equation. Okay, we're going to focus on S. Okay, so ECDSA, it's been a standard for, I don't know, over 20 years now. Before that, it was preceded by the regular version of ESA. Multiplicative groups. It's, as a signature scheme, it's been around since the late 80s, early 90s. All right. Okay, so if we take the S portion of that signature and let's rearrange it for a moment. So this is the S component of that signature. If I flip back really quickly, we're just going to take this and rearrange it, okay, and start thinking about knowns and unknowns in this equation. So when we rearrange the equation, we get something like this. And so here's the shtick. So let's just think about if we have one signature. Okay, so if we have one signature, so the I here would be either 0 or 1, depending on how you count. Well, we know what the message is. So in the attack model, the message is assumed to be public. That's the whole idea with the digital signature, right? So you're supposed to be able to present some public information on public data that shows I'm signing this document or this piece of data. So the message is public. S and R, those are just the components of the digital signature, right? So those are public by definition because those are what you attach to messages to say this is signed. So M is public, S is public, R is public. The only 2 variables that are left are K, the nonce, and alpha, the long-term private key. Both of those are secret. So we have one equation and two unknowns. So how many solutions do we have? We want to solve for alpha. How many solutions? We have one equation and two unknowns.
Sorry, what does the I correspond to what?
So since this is our first signature, you can think the second signature would be like I equals 2. The first signature would be I is equal to 1. But let's start at I is equal to. You can even throw away the I's for this conversation. So we have.
So you have a batch of several signatures.
We would, but we'll start out with just one.
Okay.
We have one signature, we have one linear equation and two unknowns. So how many solutions do we have there?
N,
Sorry?
N, that's right.
Sorry.
N solutions.
N? Yes, exactly. N. So that's really good. Most people say infinite, right? But of course, nothing is infinite in cryptography. So we have N solutions. Exactly. Okay. So, which is great, right? Because alpha is an integer modulo N. So if you're trying to guess it, those are equivalent, right? So you really can't, if looking at that equation, the best you can do is to just guess alpha, which is a pretty good, that's pretty good security wise. Because the probability that you're going to guess alpha is negligible in N. Okay, so as an attacker, that didn't work really well. We got one signature, but we had one equation and two unknowns. So, but we're cryptographers, so we have oracles, we can query stuff, we can do things. So let's query the oracle again, and we'll get another signature, and let's see what happens. Well, now we have I is equal to 1, and we have I is equal to 2. So the messages are still public, the signatures are different, but they're still public. Alpha is fixed, so that still counts as only one unknown. But the case of I, remember we have to generate a new nonce every single time. So now we have two equations, right? Because we built up two signatures, but in terms of unknowns, we have alpha, case of 1, and case of 2. So we have two equations and three unknowns. So how many solutions do we have? Still N. That didn't help us at all. That was useless. So we created another signature and it didn't do anything. I think you can see where this is going. If we keep adding signatures, it doesn't help at all. So that's part of the shtick with ECDSA. That's half of the trick of why it works. Okay. Security-wise. Okay. So now I'm going to talk about leakage, and what leakage is side channels. So sometimes when we implement crypto, different implementation aspects can actually cause parts of the internal state to leak. So what I mean, if I flip back really quickly and we talk about the scalar multiplication here, this is generally the heaviest part of the computation, and it's where a lot of engineering effort is spent to speed this up. So, but if we don't treat K, in a very engineering kind of nice way, we can actually accidentally leak bits of K as we do this entire computation. And that can happen because, if you think about mathematically, if I give you the output of KG, recovering K is called the elliptic curve discrete logarithm problem, and it's very hard mathematically. But, when you start leaking parts of K, and that can happen because when you actually implement things, you have hardware that's going to emit electromagnetic radiation. It's going to consume power. You have software that takes variable time depending on the microarchitecture state. So if any of these things can eventually work back to part of the secret nonce K, then we're leaking part of K. The partial leakage I'm talking about today, I'm not going to talk about everything. So if we have an implementation that is so leaky that it leaks all of K, that's not interesting, because then you end up with one equation and one unknown, and it's just a high school algebra or middle school algebra, right? It's not very interesting. So we're not going to talk about leaking all of K. So it's somewhere between leaking none of K and leaking all of K. That's what the talk is about today. Okay, so if I go back to the previous sort of hand waving that I was doing, we have J equations and J plus 1 unknowns, but really the situation isn't that dire. If we talk about leakage, if we're leaking part of these K sub I, so it is kind of like J plus 1 unknowns, but it's somewhere between J and J plus 1 unknowns, roughly, because we know part of the case of I. So very roughly, that's what's going to be going on. So lattices are going to be the solution that let us solve this problem efficiently. And I'm going to talk about lattices in just a moment. But the general idea, the rest of this talk is really going to be focused here. So for the example I'm going to give in the next couple of slides, I'm going to just say for whatever reason, these case of I are small. So the logarithm of them is short. So they're short for whatever reason. Just for an example, let's say that these case of I are short. They're supposed to be chosen from the range 0 to n, but let's say they're short for whatever reason. So they can be maybe 4 bits shorter than n, or half the size of n, or something like that. So when I say short here, I mean in terms of the logarithm. Okay, so for whatever reason, let's say that these nonces are small. So if we can somehow produce a small solution to this system of equations, we have j equations and j+1 unknowns. But if we had some magic box that would let us find a small solution to this system of equations, then it's pretty likely that that solution that that magic box gives us is actually going to be the solution we're looking for. So why is that? So I'm going to give you an example here of why, sort of the intuition for why lattice attacks works. So let's say n looks like this. It doesn't have to, but just for this small example, let's say n is very close to a power of 2. It's just under a power of 2. Okay, it makes the example a little bit easier. So you have those j equations, you have j+1 unknowns. How do you find one solution to that system of equations? Well, from middle school, probably what you would do is you would just pick one of the unknowns at random. And then you have j equations and j unknowns, and you just solve it with Gaussian elimination, right? So let's do that and see what those solutions would look like. We take one of them, we take one of the unknowns, we choose it at random, and then we solve for the rest of the unknowns. And let's say there's 31 of those unknowns here. So what are those solutions for those unknowns going to look like? Well, since n is like this, and the nonces are chosen at random, basically half of those nonces are going to have the top bit set, and the other half are going to have the top bit clear, because it's a 50-50 chance whether you get a 0 or a 1, right? That you would, if you just randomly choose to solve the system of equations, that's what you would expect. Half of them have the top bit set, half of them don't. Okay, so for the ones that don't have the top bit set, the next bit follows the same logic, right? So half of those are going to have the next bit set, and the other half are going to have the next bit clear. So I'm talking about this bit here. And this goes on and on down like so. So these are kind of the probabilities of numbers looking like that solution, okay? So this is what a completely random solution looks like on the left-hand side. But our solution doesn't look anything like this on the left-hand side. The reason is because I started for the assumption that those nonces, they're small. The logarithm is small somehow. So our solutions look like this because this is small. This has a smaller logarithm than the order, right? So ours look like, none of these are in our solution. So ours are supposed to look like this. So if we look at what the solution we're looking for, it looks like the one on the right-hand side. It starts with a whole bunch of zeros, and then there's finally some ones down here at the end. So this is what our solution looks like, because all of the nonces in our system of equations are significantly shorter than n. So I hope the contrast between these two examples says that if we have some box that gives us small solutions to systems of equations, then it's very likely that so this is a small solution, right? So if the magic box pops out something like this, it's almost always going to be right, because the probability of a solution looking like this is negligible in the number of bits, how short the nonces are, and the number of equations that you have. So the probability of this happening is so small. So if we somehow have a magic box to give us one or more of solutions like this, it's probably going to be one of those, okay? These are everywhere. So we have a huge bucket with tons and tons of apples, and there's a few oranges in there. And we just have to find those few oranges and then check and see if those are the solutions that we want. That's the general idea. So I'm going to get more technical now before I move on. Are there any questions so far? About what's going on here? So I've oversimplified here in this example, but at least, just trying to get at the intuition right now.
Is it a practical attack scenario? Can you somehow inject faults in such a way that the nodes would be
Short in some way? Yeah, so I'm gonna walk through some examples. So my most cited paper, remote timing attacks are still practical, is exactly shown on the screen. So it is in fact practical. One of the reasons is that a lot of the algorithms used for scalar multiplication, if you look at the pseudocode, they say you should start at the top bit that's set. So they don't say you should start at a fixed bit, they say you should start at the first non-zero bit, which is exactly that's the logarithm. And if you are able to identify that bit, so yeah, that is one example, but actually the traces I'm going to look at today are slightly more complex than the example. Okay, so I think, lattices attacks for so basically what's going to happen, we have those signatures, which are these RS pairs basically, and we have all of those and it gives us some system of equation. We have some magic box called lattices that we want to stick this system of equations into. It's going to pop out a solution that's small and hopefully that gives us the key, the private key. Alpha is the one we're looking for in the end. I don't know anything. I'm not a mathematician. I'm an engineer, right? So I try to use these lattices black box. The rest of the talk today is going to be me saying how the constructions that we get from people who do lattice algorithms, they fundamentally misunderstand the problems that we face in applying lattices. I'm going to give you 4 open problems. I don't know if any of you are starting PhD students, but if you are, you can basically take those 4 starting problems and you can write an entire dissertation on this. I would guess. Francisco, how much time do I have?
Until 12:30.
12:30. Okay, good. Okay, so lattices, I'm not going to dig too much into the algorithms that go into lattices, but just to give some examples here. So here we have a definition for what a lattice is. It looks like the picture here. So you have an n-dimensional lattice. It's an additive. Yes. So it's a subgroup of this n-dimensional space here. And so the important part is a basis B, which is defined by a bunch of row vectors that are n-dimension row vectors. Have n of them. So you can think of it like a matrix. And think of it, it is literally a matrix. And it defines a lattice as follows. So you basically can take the basis and you multiply it by some n-dimension vector z, and then you get out some point from that space. So if we look at this example, you see what's trying to be shown on the screen here. Not sure how they're doing the notation here, so it's going to. I lifted these slides, these two, so it's going to take me just just a moment to figure out what they're trying to say. Right. So, this one is invariant under transpose, so I don't know which kind of notation they're using, but well, here is one of the basis vectors. Let's call this.
It's the 1, 2.
It's either 1, 2, or 2, 1. It's one of those.
It's like not the column line, the other column line.
Okay. Column wise. So right. So 1, 2, 3, 1. This would be a basis vector here, and then 1, 2. This would be the other basis vector here. This is a 2-dimension space, right? So these 2 vectors column wise give you a basis. And then if you think about what the lattice is, it's all of the linear combinations of these 2 vectors. And that's basically what you get. So if we take those 2 vectors and we start computing all of the linear combinations of them, you get this lattice type structure. I say lattice here, it's like the stuff in your garden, right? It's like a checker, lots of dots that look in a very uniform way. That's what a lattice is. Okay, so the bases are not unique. So you can see that 4, 3, 9, 8 is also a basis here in this case. That is true. So there is one of those points here, and the other point is here. And so they're the same bases. If you can find some unimodular matrix U, that if you multiply the original basis by it, you get this new matrix B prime. the idea here is determinant plus or minus 1, so that's going to guarantee that it's invertible. So you're just poking the original basis in a certain way so that you get some different kind of basis. Okay, ignore this part here. We're going to focus on these parts here. So from the previous slide, there were 2 examples of different bases, but they were different. Let me flip back. So you had these 2 different bases. The way we're going to apply lattices is we need somehow small bases. Okay, so if we can think between these 2, the first one is smaller, and we define smaller here as the. So in terms of vectors, it's the L2 norm, so it's the Euclidean norm. I'm pointing at the rows, but again, they did theirs in columns in this case. Yeah, so it's the norms of the vectors, and that's how we define the size. So the shortest vector is going to be 1, 2. That's the shortest vector in the lattice, and the length is square root of 5, of course. And then the shortest base is, since you have a set of vectors, how's that defined? It's the length of the longest vector in the basis. Okay. Okay, so that's a couple of terms here. So somehow the shortest vector 1, 2 is magical. All right. And the shortest basis here is also somehow magical because they are short. How do we find them to be short? We don't really know yet. There are 2 problems associated with lattices that I want to talk about today. The first is the shortest vector problem. So I talked about from the previous slide, we had the shortest basis vector, but in general, if you think about all the points that are generated in the lattice, so what is the shortest vector in the lattice? So this is infinite, right? So what is the shortest vector in the lattice? In general, it's a pretty hard question. So here we have, again, we're working in 2 dimensions. We have a basis vectors B1 and B2. And it turns out that this vector here, if we look at the visual representation in 2 dimensions, this is a much easier problem to solve, okay? But you can kind of see how this is a short vector that's in the lattice. So yeah, that is the shortest vector problem. So you would be giving these 2 bases and you would, what is the, to solve the problem, it's you have to find what the shortest one is. Again, in 2 dimensions, it's pretty like you can just solve it analytically. You don't have to use complex algorithms. 3 dimensions, you can actually also solve it analytically with Gaussian methods. And then I think in 4 dimensions where it starts to get tricky. So that's the shortest vector problem. And again, there you're given the basis vectors and you're finding another vector in the lattice that happens to be the shortest. The second problem is very close, very much related. It's called the closest vector problem. It's very similar. You have basis vectors B1 and B2, and you're given the green dot here. This is not a lattice vector, right? You can see how it's kind of, they have a name B1 and B2 here, but you can kind of see that this is not a lattice vector because it doesn't lie on the right lines here. So you're given the basis vectors, you're given the green dot, and then you're supposed to find the closest lattice vector to that non-lattice vector. Okay, so in this case, kind of visually again, and even analytically, it's clearly the red dot. All right, lattice algorithms, why do we have them? How have we been using them? The classical algorithm is LLL from 1982. So the idea there is you're given a basis, and the idea is to take that basis B and reduce it to some basis B prime that is small in some respects. It's not necessarily the smallest, but it's bounding. Okay. So then once we have the basic algorithm, so this is the basic algorithm for getting the small basis. And once we have that small basis, we can use it to approximate the CVP and SVP. There's 2 different ways to do that. There's Canon's embedding technique, which is very important, and I'll talk about it in just a second. The easiest one to talk about is Babai's nearest plane algorithm. So this is basically given the reduced basis here, you can approximate the CVP with some pretty simple linear algebra. It's basically some you reduce the basis and then you apply the Gram-Schmidt orthogonalization. That's the basic idea. Now, me as an engineer, I don't know anything about, I know very little about these algorithms. Again, I try to use these as black boxes. One of the things I struggle with is if I want to solve CVP or SVP, almost none of the libraries are going to give me an API that lets me do that. So I would like to plug in, you know, I think I described the problems pretty easy here. So if I give you the basis and I give you this non-lattice vector, I would like to have an API that gives me back the red dot. Or for SVP, if I give you the two blue basis vectors here, I would like to have an API that gives me back this red arrow dot here. That's what I want. They don't do that. Most of the black box, most of the libraries you get are really solely going to be focused on the reduction part of lattices, and they're not solving the hard problems. But again, they're very closely related. And that's one of the reasons why I like the embedding technique, is because since we don't have algorithms to solve CVP, and CVP involves points that are not on they are not in the lattice, it's really hard to get libraries to work with points that are not on the lattice that you were literally working with. So what's nice about Canon's embedding technique is basically you can take that input vector to CVP and you make it part of, you add one dimension to the lattice, and that new vector that is your target vector actually becomes part of the lattice. And then you only have to solve SVP, which hopefully gives you a solution to CVP. That didn't make a lot of sense, but let me kind of wildly point at what's happening here. So we want to solve CVP, but we want to use SVP. Basically what you do, you add one dimension. So we have two dimensions here. Think about three dimensions. So there's one sticking out at you, okay? And this new green dot is now part of the lattice because it's in this extra dimension here, right? It's now actually part of the lattice. And the idea is, since it's only one step up, this is the distance of one towards you, the distance kind of from this to here and the distance from here to here, it's going to be roughly the same because it's only a distance of one. So if you think about this angle, it's probably, if you can somehow make this green dot part of an extra dimension lattice, you probably can solve the CVP with only using SVP methods. It's a really nice technique, and I think fits really well for engineers because it says that you don't need a black box that does CVP and SVP. Actually, all you need is a black box that solves SVP, and you can use a canonical embedding to convert all the CVP problems to SVP problems. Okay, that was a lot. Right, so you had LLL from 82. The embedding technique from 83, Bell-Eisner's plane algorithm for CVP approximations in 86. And you had BKZ algorithm in 1991, which is for block lattice reduction. This is very similar to LLL. What I want to say here is that the reason BKZ is more interesting moving forward, they're both classical algorithms. But the point is, when you go up in dimension, here you go in dimension, the less accurate that LLL becomes because it works on all the basis vectors as a whole, as a set. Whereas BKZ, you can take sub basis vectors. You take part of the basis and you can work on reducing that smaller part. What I'm trying to say, BKZ is generally better for higher dimensions because it can work on these smaller sub lattices, where LLL, it does everything at once. So it doesn't work very well. It works really well for dimension up to like 50 or 60, but when you get over that, BKZ algorithm is where you want. All right. So I promise this is my attempt at a little bit of math today. I don't have too many equations in my talk today. And I don't want you to focus too much on the values that are there. I'm going to try to point out what is actually interesting from all the equations that are on the screen here. But I need to go step by step here so that we understand what is happening. So the first lattice attacks on digital signature schemes, they emerged around 1999, 2002. that looks like a 3-year gap, but it's not really. Like, this was a journal article, and this was a preprint when Nigel was still at HP. Yeah. Okay, so the first part, if we're going to attack digital signatures using partially known nonces, then we have some kind of leakage, side channel leakage that's happening on those nonces. Okay, so here's the K sub I, here's the nonce, and we're going to split the nonce. We're going to think about the nonce. It has 2 parts. Okay, A sub I, which is the part that you leaked somehow. So the least significant bits, we're going to say that these are leaked. The A sub I are known, excuse me, and the B sub I are unknown. So we've somehow broken up the nonce into, we know some of the least significant bits, but the most significant bits B sub I, we don't know these. These are unknown. So we have some unknown part of the nonce, and we have some known part here, and they're on, you weight them based on where exactly they are in the scale. This is a typo, the W sub I. I'm sorry that it's W sub I. It should just be W, and this should be just L and not sub I. So what I'm trying to say here is, in this model, the original one from around the turn of the century, in this model, every single nonce is leaking a fixed amount of bits. So L might be 4, in which case A sub I is 4 bits, and you leaked 4 bits in that signature. You would somehow try to build up. In that case, you would need, I don't know, 20, 30 different signatures, more than 20. You would need probably about 40 or 50 signatures to actually recover the entire key. In that case, you would build up multiple signatures. Okay, but nevertheless, let's step through some of the rest of the equations. Okay, so by definition, because of how the nonce is, it's between 0 and n, right? But if we look at, now we're going to start breaking up this case of I. We know parts of it and we don't know parts of it. So if we focus on the unknown parts, then this is the inequality, right? So this is just targeting the most significant bits here. So you're dividing by W sub I, which makes perfect sense, because if A sub I, for example, is 4 bits, then B sub I is 4 bits less than n. We're going to define a couple of different values here, T sub I and U sub I. Hat U sub I, sorry. So the point with T sub I and U sub I is to manipulate the equations for S in the digital signature so that we can express them in terms of these constants, not constants, but these variables in terms of only known values. So if we look at what's happening here, T sub I, it's a function of R sub I, which is known in the signature, the weight, which is known from our side channel, and the S sub I, which is part of the signature. So that's all known. T sub I, these are known values. This notation is this modulo n. So it's reduction from 0 to n minus 1. U sub I is the same. A sub I is the part that we knew from the leakage. H is the hash, which is public, and S is part of the signature, which is public, and W sub I we know from the side channel. So T sub I and hat U sub I are completely attacker known. So if we take this equality B sub I here and we rearrange, basically we substitute in the equation for S and solve it for the long-term private key alpha, we end up with this inequality here. And right, so it basically says that alpha times the T sub I, which are known, minus hat U sub I, modulo n is also 4 or a number of bits less than the group order. Okay, so now we're going to play some tricks to kind of straddle. Instead of 0 to n minus 1, we actually want to straddle the origin, because we're talking about sizes and not necessarily it's about sizes. So instead of working from 0 to n minus 1, we might want to work with the negatives as well. So it's like negative n over 2 to n over 2. These are like small minor details for why we're using U sub I instead of hat. The point is this equation for B sub I here. We look at B sub I, this inequality. So we have alpha times T sub I minus U sub I. Alpha we don't know. This is the long-term key. T sub I is completely known to the attacker, right? That's from here. U sub I is completely known to the attacker. And here we're talking about reduction from negative n over 2 to n over 2. So it's the absolute value. And this is the whole point of lattice attacks, okay? Somehow we have been able to find an inequality for alpha, which is the long-term private key. These are known, so we have, this is the only unknown part. And we bounded this, we said that, you know, without any information, how would we find information on alpha? It would be any random number from 0 to n, right? But using these inequalities, we've been able to bound it by saying that we have some function of alpha that is less than, so the number of bits of unknown in alpha here is w sub I, it's less than n. And this is the magic right here. Because if we didn't know any information, then this inequality should be less than or equal to less than n, basically, is what you would end up with. But we've been able to come up with an inequality such that we've bounded the unknown part of alpha to some certain range, and that's the whole magic right here. We have some integers, lambda. These are the multiples of n when you actually multiply this out. So if we're not talking modulo n, we're talking as integers. Okay, so if we take alpha times t sub I, subtract off u sub I, and subtract off some multiple of n, we look at the absolute value. It also has the same bound. So how do we use lattices to find? So again, we want some small solution. So here what's happening, another way to look at this is these u sub I. The u sub I are approximating alpha times t sub I. So if we just choose u sub I at random, we wouldn't expect this inequality to hold for any particular reason, right? But since we know some information here, basically what we're saying is that the closer this is to 0, the better the approximation. So this is what the basis looks like on the right-hand side. We're going to use lattices to find small solutions to this system of equations. And this is how it looks like. The idea is basically we want to end up with this relationship on the bottom right here, which is we have a vector x times the basis minus the vector u gives you y. Basically, this is just a very simple system of equations. You're taking the equations from here and packing those so that you can work with vectors of equations instead of individual equations. Right. So if we look at what we know here, x times b, the basis matrix B, everybody knows. So everybody knows this. There's no secrets in this basis matrix. The vector x is secret. So we don't know what the lambda are. And we certainly don't know what alpha are as the attacker. We would like to learn what that vector x is. U, everybody knows U. This is a public vector. So and y, again, it's unknown because it involves alpha. Don't know what it is. So we know the basis B, we know U, and we want to find x. And in the end, this is an instance of the closest vector problem because U is right. We want to basically give the inputs of this basis B and the vector U, which is a non-lattice vector, and we want to find x. That's the idea. And it should be fairly small because of the y portion.
So the same secret alpha is embedded in both sides, in the coefficients x vector as well as in the y.
That's correct.
Okay. So it's somewhat even special than the general.
It is very, yes,
right?
it is. It's a very special case. Okay. I was given a talk about lattices a long time ago in Bristol when Nigel Smart was still at Bristol. I don't know. I definitely didn't know much about lattices then. This was like 2011. And I said, one use of lattices in cryptography is finding small solutions to systems of equations. And I don't know if y'all know Nigel, but anyway, he interrupted immediately and he said, actually, the only use of lattices in cryptography is finding small solutions to systems of equations. Okay. So that's the magic. We've known this for like 20 years, how to use this. And I think when I started, I was the first one using lattice attacks for combining real side channels with lattice attacks back in 2008 is when I started this. So you can imagine me as a PhD student, I'm trying to utilize what these people from theory side, what they've given me. So I have some side channel and I'm trying to make it match the characteristics that are shown here so I can make stuff work. I want to be able to recover keys. I don't know how to parameterize anything. I don't know how to choose the dimension D here. I don't know anything. I'm just an engineer. So I stumbled through it and I'm still stumbling through it, to be honest, many years later. So I'm going to talk about a lot of the problems that pop up when you take that theoretical model. This is a real side channel trace shown on the screen here for what scalar multiplication might look like. So first, before I go through the actual trace, I want to look at some code and kind of show you what this looks like. So that's a trace from OpenSSL. So I'm going to go, it's not my code, but I'm going to bring up the code and we're going to look at how an implementation might actually be leaky. And I'm going to go through this really fast. I apologize if it's maybe a little bit too fast for the folks on the theory side, but let's see. Going. Okay, so here's the main loop. So the idea for scalar multiplication with OpenSSL, it's a double and add algorithm. So it starts from the most significant bit, that's what K is here, and it works down to the least significant bit. At every single step, it doubles, and then if the digit is non-zero, it's going to add in some value from a pre-computation table. How that's fitting into the slide, to the code here. So basically, it starts the loop. If the point's infinity, you can just skip it because if you double the identity, you get the identity back. So it's skipping if it's infinity, but if it's not, it needs to double at every step. And then I, you can think is zero here. I need to scroll down some more. Right. So if the digit is zero, it's not doing anything. It's just skipping and moving to the next bit. If it's non-zero, it's going to do a point addition. And it does a whole bunch of logic to figure out what that point addition is supposed to look like. It checks if the digit is negative. I'm going to talk about that in a moment. Sometimes it inverts the point if it needs to, depending on the signs. And eventually, way down here at the bottom, even more, it does the point addition. Okay, so eventually it gets down to that. So if it is infinity, it just sets the point, but if it's not infinity, it does the point addition. You have some accumulator here. So this does R equals R plus some value, magic value, depending on the digit. Okay. My point is, so if you would think about this loop leaks all over the place, this is really bad code in terms of side channel resistance. You cannot skip operations. You cannot do memory resident lookup tables on secrets here, just to name. And then we started at the most significant bit set. So that's at least 3 or 4 different vulnerabilities in this one piece of code. But generally speaking, from the side channel, what you would expect to see is a bunch of doubles and adds. That's basically what you would expect to see. And if you can somehow pull out that sequence of doubles and adds, it's going to tell you something about the nonce that was actually used. So here's a trace, a real trace against the code. How this trace exists or why it exists doesn't really matter. Here it happens to be timings, a very specific microarchitecture component. The trace is actually much longer than what's shown on the screen here. So I would say a typical trace is about 10 to 15 times the length of what's shown on the screen here. But I'm focusing on a very small portion of the trace here just to give an example. So we're trying to find that sequence of doubles and additions here. So just to point it, well, it's already tagged here on the slide. So you can see that the point additions are in blue and the point doublings are kind of in yellow. They come in pairs. Very generally, if I was trying to extract, so we go from this very rich side channel data to extracting the sequence of curve operations, which I guess, so very roughly what's happening here, I'll just point, we have a double, then there's an add here, And we kind of missed the double here, but it's there. There's a double, 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 add, double, 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 add, double, 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 add, and so on. So if we look at that sequence, write it down now. Double and add, and then four doubles and an add, is that right? And then another 4 doubles and an add. And then the 7. Add, and then it was 4 doubles and an add, right? We're able to extract from, so we have all this crazy data, and again, the trace is much longer, but in the end, those are just, we can throw away all that data with very fancy signal processing, and we end up with this sequence, okay? So now we work with the sequence, we don't work with the actual side channel data. So we throw that away. So what does this actually mean in this case? So if we see a double and add, this tells you that something is, I think maybe it's easier to start working from here. Double and add tells you that there is some kind of digit. I'm going to say D sub 4 for digit. There's a digit. So so that covers this. And then we have a double and no add, so it's a 0. Double and no add, it's a 0. Sorry, double no add, so it's 3. And then we have a double and add, so we have another digit. Don't necessarily know what it is yet. And then the same thing again. The digit corresponding to this one. And then we have, yes, exactly. And then a digit again. And then we have missed a double, didn't I? Okay, so then it's zeros and D's like a whole lot like. And then we have another digit. Okay. So in terms of recovering key material from that nonce, we know a lot of these 0 positions, okay, but those actually happen to be part of the representation, and I'm not going to go too much into that today. But if we look at what the digits are in this case, it's not binary. It comes from a set that looks like this. In this specific case, that's what we know. So I'm going to pause here for a minute. So we've clearly learned a lot about this chunk of the nonce, right? We know where a lot of these zeros are, but some of these are kind of artificial, like these 3 don't actually count. A lot of these count for various reasons, but when we look at the actual digits, it's not like it's a 0 or a 1. It's much more complex in this case, okay? Because there's this pre-computation happening. So we know it comes from, it takes one of these 8 values, basically, plus or minus all of the odd values in some 3-bit range is basically what you get. We can't distinguish between what is happening. We know it's one of those 8, but we don't know anything else about it. We just know that it happens to be that. Right, so now if I go back, yeah, so I think that's a good, so sorry I went through that fairly quickly, but this is basically generally the idea of what kind of data to expect from practical side channels. Now, we have this practical side channel, we have this information, partial information on the key. Now we're going to try to work backwards and try to fit that into all the crazy lattice stuff that we have. And here's the problem. So the theoretical leakage model, you have one known chunk and one unknown chunk. But I hope you can see here, we have lots of known, and there's a ton of known and unknown chunks. Here's a chunk, here's a chunk, here's a chunk. For the full trace, there would be like 50 of these. So if I go back to here, the original, I would say, I'm not trying to criticize the authors here in saying that they're saying that all the nonces leak in the same way. I think this is the obvious way to model leakage without any specifics about an implementation. This would be the obvious way to model it, but I cannot plug this in to that. It doesn't work that way. I don't know how to use it. So what am I supposed to do? I do really dumb engineering things, which is this. I oversample and ignore extra information that does not fit the model. So what I'm saying in this case, I would just throw away all of that information. Unfortunately, it's really good information about the key, but I just throw it away because I can't use it. And then I just use this one chunk and I just say all that stuff is unknown, which isn't really true. I know part of it. So I just focus on this one chunk. So we're throwing away all this trace information because it doesn't fit the model that we have there. Problem 2, expectation versus reality, errors, noise. Theoretical leakage model. I think it's very natural to assume that there are no errors. I don't know where you would start from a theoretical analysis. I think this is always the case. You just assume that the information you have is accurate. It's a very natural way to start. In reality, it's not accurate at all. So we almost missed this double here. If I had the longer trace, I'm sure I could find lots of errors here. So the information we have is imperfect. How do you deal with that imperfect information? In a really dumb way, we basically oversample. We run the lattice algorithms. If it pops out the key that you want, yeah, you're done. If it doesn't, this is what we do. We take another random subset of those traces, we run it, and we see if it pops out the key. So this is what I've been doing. Was the first methodology for how to work with errors. I call it a methodology, just picking random stuff. That's all we have. It's 15 years later, and this is still all we have, just picking random stuff. It's terrible. Okay, problem 3, accuracy depends on row order. This is the LLL algorithm, the one that does the reduction. I'm not going to go into this at all. This is Gram-Schmidt orthogonalization here. The point that I want to make from this slide is you input a basis, which is n different basis vectors, and you iterate through them from top to bottom. And then you're adding and subtracting different parts of this functions of the scalar to the basis matrix, okay? And then sometimes you're swapping, you take some maximums and you're swapping in certain points. The point I want to make from this slide is that the quality of your reduction and your ability to find the key depends on the order in which you have plugged in the equations. And that should like set off all sorts of, that doesn't sound right to me, alarms to you, because how can that, the order in which I have plugged in these equations, the security of your private key should have nothing to do with the order of different equations that, whether you sign one message first or the other message first makes no difference, right? So how can so to me, it was always very frustrating to deal with that fact that the quality of the reduction depends on the order in which you plug in the equations. And of course, not knowing how to deal with it. I've observed this, okay? So I know this is true. How to deal with it, I do very stupid things, like I just shuffle the equations and I try to solve it that way. So that's what I have, because that's all, I don't know how else to deal with it. Okay, the last problem in this area, iterating. Okay, so we gather all of these traces, we extract the sequences like this, we extract the partial key information, and we have all these signatures. You construct your lattice, and then you use one of those algorithms to solve or try to solve SVP or CVP. So it pops out a key. If it's great, awesome, you are done. If it's not, what do you do? Like, what are you supposed to do? You've run the reduction, but it popped out the wrong key. So a lot of people, I think from the theory side, what they say is, well, I'll just run the entire attack again. I'll get some more traces and we'll run it again. But I don't think that that's really the best thing to do, honestly, because that's still very good side channel information that you had. So why would you just throw it away? So there has to be something better than starting from scratch. So of course, what I'm doing in a very engineering way is you oversample and you take a random subset of those and you just try it to solve it, to solve for the key again. All right, so those are the 4 problems, I think, in my opinion, from the engineering perspective, on how the models that we have in the black boxes that I have to use with lattice algorithms, they aren't fit for purpose for the kind of side channels that I have. And I have to do very silly things to make my data fit what those black boxes expect, okay? So those are the 4 problems in this area. This is, my last slide. So this is supposed to be you here saying, you dumb engineer, are you really just picking random stuff and doing it again? This is me beating my same drum for 15 years and publishing the same paper saying, please give me better algorithms, math people, please give me better ones. And I keep using them anyway when I don't get new ones. And this is me again, pointing at the math people saying, you really want me to use, I'm just doing it like this. And then, here's the mathematicians looking very poorly at me trying to do linear algebra. So, so that's the talk. I'll take any questions if you have any.
So you talk about this discrepancy between the theoretical model and what you get right in problems 2 or 3. So like the example you write on the board. So how in practice, how far is it from? Like, is it the discrepancy really big? Or
Yeah.
really minor?
It's a really good question.
Okay.
And it kind of is bittersweet, I would say, this discrepancy, and I'll explain that too. So how do you pick the dimension? So here there's a value B for how many signatures you need, okay? And roughly the rule of thumb is all the amount of secret information that goes into the lattice. So all these known bits that you've been able to glean. So the sum of the sizes of these A sub I, this needs to be roughly the size of your private key, which I think makes sense because you've kind of solved for information and you wouldn't expect to be able to magically solve if you only know half of secret key material. You wouldn't expect it. So ideally, each one of these adds extra bits. So every single equation, like, you get maybe, I don't know, 3 bits here, 3 bits here, 3 bits here, 3 bits here. So for each trace, you could be getting up to, 100 and something bits in a very rich trace, like I showed on the screen. Like and instead I throw all that away and I get 3 bits. So it's about a factor of, you can do the math, but it's like 15 times, I guess, more traces that you need. It's bittersweet, I would say, because it also plays into the errors, because if I'm throwing away all that information, then actually it doesn't matter if it's accurate or not, right? So it's a weird situation because when you're only using part of the trace, you don't really care about it. You only care about the accuracy of this part, right? So it's a very strange, the more information you try to use, the more likely it is that some of that is probably wrong. So yeah, and that's the game as, cryptographers, what they try to do in academia is you want to push down the number of signatures that is required for the attack. That's the metric at the end. So clearly from a theoretical perspective, using all of the key material per trace is good to do.
Question. So you were saying that your WIs are in fact constant, right? You have each time. So I'm kind of surprised that there's nothing that's been done for the non-constant from a mathematical point of view. There's not particularly any difficulty.
So it's definitely a good observation. So some progress has been made on these 4 problems over the past 5 or 6 years. And that one has actually, there's been a lot of progress made on varying the W sub I. Well, so I told you that this was a typo and they should be a fixed weight, right? So in reality, what we actually have now is we're able to vary the W sub I's. So instead of having them at a fixed position, we can utilize more leakage. But still, it needs to be a known part versus an unknown. So the W sub I's are now per equation instead of fixed per basis. But that still doesn't let us use significantly more of the trace. So the very first lattice attacks, for example, when W was fixed, it was say 4 bits or whatever. If you didn't have 4 bits of leakage, no matter what, you just had to throw away the signature. So you might have, you think about probabilistically how, the least significant bits, 50-50 if it's going to be odd or even, and then you get some, geometric distribution down from that. It's basically the probability of leading bits is trailing 0 bits is negligible in the length of the run, right? So if you're saying you need 4 bits that are clear in the least significant bits, you're only going to get that in 1 out of 16 signatures. So those other 15 signatures, no matter what they have, you just toss them and you just take the 1 signature. That's where we started from. So things have gotten slightly better in terms of the weights, but yeah. So varying the weights, this happened maybe in 2015. That was again a paper by Nigel Smart.
Just a simple question. So you're saying in the end what you're doing is basically choosing random cells, reshuffling them, and then running the algorithms again. So in your own opinion, all the theory we have, is it kind of useless, or so where is the problem?
So I've developed kind of tricks using the black. I don't think they're useless. Really what you want to happen. So we run the reduction and then we use one of the approximations to solve CVP or SVP. The hard part is the reduction. The reduction is polynomial time, but it doesn't make any sense to look at this algorithm, but LLL is polynomial time, but it takes a significant amount of time. What I would like is so what is happening right now, if it doesn't work, we ran the reduction, we tried the CVP approximation, it didn't work. And then on the theory side, they say, throw that all away and start over. But you have this nice basis that you've reduced, and that took a lot of work to do that. So I don't think, so there has to be some connection, I think, from the theory side to say, use that reduced basis, but maybe, I don't know, introduce one new lattice vector, two new lattice vectors, basis vectors, sorry. So like, there has to be something to leverage the work you did already in the next, it's okay to throw away some stuff, but you don't have to throw away everything, I guess is the point. And there has to be some kind of theory that would help there in terms of moving from, iteration I of the attack to iteration I plus one with something other than a clean slate. I guess there should be some kind of theory to help with that, because you get very strict bounds from the output on this basis. So it's really a shame to throw it away, and I wish someone would tell me how to use it. So I don't think it's all useless. So having things like bounds on LLL is really important. But in terms of the overall attack, I feel like sometimes from the theory side, people are missing a lot of the practical considerations that we have to deal with. Another one that is missing, I think, from the literature is how to choose the dimension, like how many signatures do you need? I said the rule of thumb was basically you want to have nonce information that sums up to the size of the private key. But that's just a rule of thumb. Like, does it get better if I add more equations? I don't. It's a trade-off, because the larger your lattice gets, the more inaccurate the reductions get. So yeah. It would be really nice as an engineer. I love tables, so it would be really nice to go to a table and say, this many bits, I need to mention that. I would be done. That's not what we have.
Is there some other crypto algorithm?
Yeah, really good question. Basically, if it's an algorithm type or similar algorithm, it's going to apply. So if I look at this equation here, in the 90s, a whole bunch of these signature algorithms popped up, some of them by my advisor, Newberg-Ruppel signatures. So you can apply this to DSA, ECDSA, and all of those discrete log systems are very similar. So Schnorr, Elgamal, what else? There's the Russian variant of this digital signature scheme. So I would say in general, if it's nonce based, it should be able to be applied. So things like, even with the more modern like Bernstein stuff like ED 25519, you can apply it in those cases because they're very similar. I also skipped an entire family, so you can actually apply this to RSA as well. So if you are leaking parts of the exponents for RSA, With RSA, the exponents are fixed, so they don't change every time. But the idea is if you're able to leak enough information, it also, in the end, it turns into a lattice problem. It's a little bit different than what I've shown here. And you don't build up equations, you build up confidence in the one equation that you have, basically. So you can apply it to RSA, I know, and I know that you can apply it to almost any discrete log-based crypto system. You cannot apply it to any kind of keyword like Diffie-Hellman. You can't apply it to Diffie-Hellman because for Diffie-Hellman, you don't have linear equations. You just have group elements. So there's really nothing to work with in the Diffie-Hellman case.
I have one more question. How is this? I'm sorry, because we have another talk by Dr. Phil the other Friday. So how is this attack better than the timing attack, the remote timing attack that you presented on Friday? Like, is it has more applications? Because basically it is also using the leaky implementation of the point multiplication function. So
Right. So I'm such a hack. So they're the exact same. They're exactly the same. So the only difference is this is kind of how I generate papers, but like go back to the trace. This is not a port smash trace. This is flush and reload. So again, I think I mentioned like one of my templates for a paper is I have these known vulnerabilities that I use, and then we have something, a microarchitecture technique. In the port smash paper, it was that new side channel. In this one, it was trying to do something better with flush and reload, I think with some degrade strategies. So you have kind of small, I don't want to dump on my own work, but fairly shallow contributions in lots of different areas. And then to bring them together in one paper, you kind of cross-cut all of those areas, and somehow that's enough for system security papers to publish. But yeah, to answer the question, it's not different at all. It's the same things.
basically, probably this one is more applicable independently of the architecture. So it's more generic.
Yeah, correct. So all the lattice, what I can do with black boxes and lattices, I try to apply it as much as I can again and again, because I already have machinery for that part. So I already know how that part of the attack works.
Okay. So thank you. Actually, I haven't checked if we have questions from the audience, but I guess we have an audience. Oh, Eduardo. Hi, you have question?
No questions from me, but thank you for the talk, Billy. It was great to see you and to listen to your talk.
Yeah, thank you very much for attending.
Okay, so if we don't have questions, then let's thank the speaker again. Thank you very much. And so see you at the next Crypto Cafe in 2 weeks. Thank you, bye-bye.
Thanks, everyone.
Thanks.